Hello everyone, today we have Shubhayan Sarkar, who is my PhD student at our institute. So Shubhayan joined the group in 2018, no?
Mm-hmm.
Has been a student for 3 years already. And now he's finishing his research and going to write the thesis this year, maybe, or not? Or next year, at the beginning. And he will tell us about certification using quantum certification using quantum theory. Okay, you can start, Shubhayan.
Thank you, Remik and Miha. So I will begin my talk. So today I will be presenting on some of our recent results, which is on certification of quantum systems using quantum steering. So let's begin. So let us look at the quantum steering scenario. The scenario is very similar to Bell scenario. There are two parties, Alice and Bob. There is a preparation device. Alice receives one system from the preparation device, Bob receives the other system, but the difference here with Bell scenario is that Alice here is trusted, which means that we can assume that Alice performs quantum measurements and she receives a quantum system of some known dimension. So now Alice asks Bob to perform some gives the input to Bob, and Bob performs some measurements based on those inputs. And depending on those measurements, we can say that some system can be prepared on Alice's side, which are denoted here with this sigma by's, which are known as assemblage. So these are like some unnormalized states, but since Alice is trusted and she can perform quantum measurements on her system, she can do a full tomography on this assemblage, and she can reconstruct this assemblage in a way. So we can also look at it in the picture of Bell inequalities using these joint probabilities, where let's say that Alice performs some measurement AX and observes an outcome A, and Bob performs some measurement BY and observes some outcome B. Then in terms of this assemblage, which I showed before, is this joint probability is just given by this. And if you express this assemblage depending on the state which is shared with Alice and Bob, which is this row AB, then and the measurements which Bob choose, which is like B by B. So then we can, here the joint probabilities is given some by this. So now it turns out that there exists some sets of quantum correlations which cannot be reproduced by any local hidden state model. I will come back to it again in the later slides, but it's like an equivalent to saying that there is no classical model which can describe Alice's assemblage. So in this scenario, which I showed before, a simple steering inequality can be constructed using these semi-definite operators, and you just have to sum it over all the inputs and the outputs of.
So Shubhayan, maybe I missed it. But did you give like a definition of steering, or entangled that is steered and so on?
Yeah. So no, I didn't say it. So I will say that. So what I mean by quantum steering is that depending on so if Bob performs some measurements on his system, so can it somehow bring a change to Alice's system. So that's how you see it, that if let's say that these are some states which are prepared on Alice's side, so if these remain same independent of whether Bob performs the measurement or not, then we say that it's non-steerable, the assemblage is non-steerable. But if Bob performs some measurements and there is an update of this assemblage depending on the measurement, then this assemblage is steerable.
Right, and maybe I'm like, and you assume some possible like a joint randomness still between or.
So in the standard scenario, there is no such assumption. Like
okay.
Yes, but Bob has to like there is always this freedom of choice assumption where they have to like randomly choose some measurements.
Okay.
Yeah. So as I was saying that we can construct a very simple steering inequality, which is like just a linear function of this assemblage with some positive semi-definite operators. And since they are like measurements which are performed by Alice, then they have to sum up to identity. Now if this steering inequality is violated, just like every witness, it means that this assemblage is steerable. But the reverse might not be true. That is, that if it could be that some assemblage doesn't violate this inequality, but you might find some other steering inequality which can be violated. So in that sense, you cannot say that if you don't see a violation, you cannot say that whether your assemblage is steerable or not. But if you see a violation, for sure, you can say that my assemblage is steerable. So coming back to what is meant by local hidden state model, what it means is that my assemblage, which was the set of these unnormalized states on Alice's side, can be written as a probability distribution over some states rho lambda, which belongs to the Hilbert space of Alice. So for example, if you take separable states, then so let's say that I have my like 0, 0, which is shared with Alice and Bob. So then this assemblage is always like the 0 state. So it doesn't matter what lambda is, but it will always be like 0 state and independent of whatever Bob performs, whatever measurement Bob performs. So now, for our purpose, we take the inspiration from Bell's scenario, and we would like to express this steering inequality, which I showed, in terms of correlators. So for this, what we do is we construct an operator like this, which is like a Fourier transform of the measurement operators of Alice. So also then we expand the assemblage using the measurement operators of Bob. And again, we express these measurement operators of Bob using a Fourier transform like this. What we get is like, we can write the steering inequality in this correlator picture. It's like expectation value of the tensor product of two matrices. So for projective measurements, what you can see is that if these FAX are actually projectors, these AKX are actually just a diagonal matrix where the eigenvectors are these projectors. So then these matrices are actually unitary, and also what you can show is that AKY is just like I have removed this indices over like 1y, so but actually it's like AKY is A1y to the power k. So now we consider the most simplest steering inequality, which was constructed in.
Can I ask? So can I ask on the
yeah.
So if I understand what I mean, the first not only about steering, like so you have.
Sorry, I can't hear you.
You can't hear me now.
Now it's okay. Yeah.
Right. Apologies for that.
Yeah.
So like you have some projective measurements.
Yes.
Like rank 1, and you kind of formally you construct unitary operations that are like Fourier transforms of those measurements, right?
Yes, sure.
So like and what is the like a benefit, like so like technically what is the benefit of that? Why not stick to original? Yeah.
So I would so technically, so I can show you that for self-testing, it's much more beneficial to actually consider this picture rather than the picture of joint probabilities. But if you say just in terms of inequalities, why is it beneficial? I don't know, because anyway, both of these pictures give you the same details about what is the state and the measurement. So yeah, in terms of self-testing, it's much more beneficial because we have some kind of like, which I will show you, like using this inequality how we self-test, and it's much more simpler to actually consider this picture rather than going to the probability picture or this assemblage picture for specific to self-testing.
Can I make a comment?
Yeah.
So,
Sure.
So the first thing is that you can, for any measurement, you can use this Fourier transform to represent it as a set of observables, let's say, which will not be unitary if the measurement is not projective. Okay, if it's projective, then you get a set of unitary matrices. So this construction is more general than what Shubhayan said. And the other thing is that the benefit coming from this representation is that we want to construct inequalities in which each such correlator or expectation value is 1, okay, for the maximal quantum violation. Okay, and then it's very easy to compute this maximal quantum violation, and then it's very easy to get the self-testing, not easy, but easier to get the self-testing statement, okay, from that.
Mm-hmm.
So that was the motivation.
Thanks.
Okay, so now considering the simplest theory inequality, just like in where Bob performs like 2 measurements and the measurements are like 2 outcome observables. So we have inequality something like this, which was like found way back in 2009. So what it turns out that this the maximum quantum value of this is actually the algebraic value, which is just 2. And for instance, this can be achieved by the maximally entangled state, and if you choose your measurements B1 to be sigma z and your B2 to be sigma x, you can attain a value of 2 for this state inequality. Now I will say what is meant by device independent certification. So let's say that I have been given a device and the manufacturer promised me that this device performs entangled measurements. So how should I verify it, or should I just trust the manufacturer? So the first idea would be, which is not good, is just to break the device and I can check the source. And if it's like a Chi2 crystal, and then okay, at least I have some indication that it gives me entangled photons. Or I can do quantum state tomography, but then I need to assume some dimension, or otherwise the amount of resources. And if it's like for some higher dimensional state, the amount of resource which will be required is quite a lot. But the best idea would be to find to calculate the joint correlation, is to measure on the 2 subsystems which is generated by these crystal, and then just look at the joint correlation statistics and try to put those statistics in some Bell inequality. And if those statistics are violated, then we can for sure say that this state is entangled. However, the other way is not true, that it might be that the state is entangled, but you might not be able to find some Bell inequality corresponding to it. Yeah, so now we look at what is meant by one-sided device independent certification. So in fully device independent certification schemes, you don't assume anything on device apart from the fact that the devices work via quantum theory. And there are some other assumptions, like the parties are locally separated, and yeah, like no signaling. So given these assumptions, like this device gives you some set of statistics, then up to some local, and then just looking at these statistics, I can tell up to some local unitaries and some presence of some extra state, I can say that my what is the underlying state and the measurements on which these devices work on. So in one-sided device independent certification, there is this additional assumption that Alice is trusted, which means that the measurements which is performed by Alice is known, and also you can in some cases, like the dimension of the state which Alice receives is also assumed beforehand. So how is it done? So first, a state inequality needs to be maximally violated by some state and measurements. And then if you could prove that up to some local unitaries and the presence of this extra state, your realizations are unique, then your statistics would certify that these are my ideal state. The state which is there is the ideal state and the ideal measurements. So now let's take a very simple example to see one-sided device independent certification scheme. So again, going back to the simplest steering inequality, what was proven in these two papers from 2016 is that up to a local unitary, you can prove that the state which is shared with Alice and Bob is the maximally entangled state with some junk state, and the measurements up to some local unitaries is your Pauli Z and Pauli X matrices given your given this steering inequality is maximally violated, which is like the value is equal to 2. But however, this was proven in the assemblage picture, and it was a bit complicated because you had to construct these isometries and quantum circuits to get this value to prove this self-testing statement. However, what I will show is a very simple proof to get to these realizations. So now let us say that my steering inequality is maximally violated.
Can I have, sorry?
Yes.
Can I have a kind of silly question? So in standard CHS-H Bell inequality, I mean that also gives you self-testing, right? Like you have 4 correlators,
yes.
Right? Okay, I don't know the state of the art, but I would guess that probably you cannot do with 3 correlators. I don't know, maybe you can. I never saw. But so here for sure I never saw with 2 correlators, right?
Okay. Yes, in the Bell scenario, yeah, there is so you cannot do it with 2 correlators, but with steering you can actually do it with only 2 correlators.
So just intuitively, I mean, okay, I guess this is because like Alice is trusted.
Yes, exactly.
But like I mean, but aside from, I mean, for sure it must follow from this, but is there some intuition, like, yeah?
So you mean to say like, why do we need like more correlators in the Bell scenario than steering scenario? Oh, okay. So, so the first thing which I would say is that because in the steering scenario, we assume that Alice performs quantum measurements, but in the Bell scenario, it's not necessary that Alice has to perform like some quantum measurements. She can perform like even some classical measurements even. So yeah, so I would say this is the reason why we cannot, why we need more correlators in case of like in case of Bell scenario. Yeah.
Thanks.
Yeah. So now I will just show a simple proof of one-sided device independent scheme. So now let's say that the steering inequality is maximally violated, which means that you reach a value 2 for the steering like the steering witness. So what it means that because this is like the algebraic bound also, it means that individually these terms also has to be 1, as Remik was telling some time back. So this implies that each of this term is 1. And now now let's say that there is some state which is psi AB, which is shared with Alice and Bob, and then you can actually say that this equation holds from here and also this. Now you do a simple operation of like multiplying with sigma z on both sides, and then because BI's are unitary matrices, you can do an operation like this. And then what you can prove is that when you have a statement like this, okay, and then what it gives you that over the support of Bob's Hilbert space, you have a condition like this, that the anti-commutator of B1 and B2 is actually 0. So, and you can, from here, you can show that up to a unitary transformation, the only measurements which satisfy this is like sigma z times some identity, and and your B2 is like sigma x time identity. Now putting these measurements back into these equations and taking a general form of the state, we can actually prove that the state is like 5 plus. So the junk is missing here. So actually there should be like O times some junk. So people ask me quite often that why do you use like quantum steering and not Bell scenario? So there are like a few motivations to do this. So the first is that there exists. So our aim was here to find a general scheme to certify any sets of incompatible measurements in a device independent way. So, but there exists some sets of incompatible measurements which do not give rise to any Bell non-locality. So, for example, it was shown in this paper in 2018. So it was proven for POVMs, but yeah, it was known that there is always a one-to-one correspondence between quantum steering and measurement incompatibility, which was like proven in 2015. So, but we thought that quantum steering is a better candidate if you want to like self-test any sets of incompatible measurements. However, it turns out that we cannot do it for any set, but I will come back to it later. So also some quantum tasks like one-sided device-independent cryptography use quantum steering as a resource. Also, for all practical purposes, demonstrating quantum steering is simpler than Bell non-locality because Alice is trusted and the robustness of such protocols are also higher than Bell scenarios. Than protocols which use Bell scenarios.
Sorry, can I have a question about this motivation regarding incompatible measurements? Just wanted to check if I understand well. So, like, I guess there are scenarios in which you can self-test informationally complete measurements. Is that the case, right?
Yeah. So I mean, yeah, sure.
So if this is the case, like, why, in a sense, by doing self-testing of those particular informationally complete measurements, you can sort of self-test. I understand, like all the measurements that, like, you can have more measurements in your setting. Then from just tomographic reconstruction, you will get them like up to isometries, right? So in this way,
sure, this is also true, but like in the Bell scenario, you can only self-test projective measurements. But like for POVMs,
so here you can directly self-test.
So here for our case, we consider projective measurements for like the work which we did. But like if you say that if you want to self-test any informationally complete measurements, I guess there are POVMs also, right? So
sure. I mean, okay, my question was more like if you self-test, let's say, a bunch of projective measurements that together are informationally complete, then even if you have more measurements in your scenario, right?
Sure.
You'll have information about them. You'll self-test them anyway, right? Whether they are compatible or not, they can be
sure. Completely.
Right? So,
like for higher dimensions, there is no such scheme till now. So for qubits, there are like you can actually self-test. In fact, every qubit measurement can be self-tested, but for d equal to 3, there are some schemes, but for higher Ds, there is only 1 or 2 schemes which can actually self-test.
I see. Thank you.
Yeah.
So kind of using of steering and this trust in ours allows you to sidestep this stage.
Yes. So going to the first part of our work. So the scenario that we consider is that there's a preparation device. There is Alice, there is Bob. Alice receives like n inputs, and Bob also receives n inputs, and each of these correspond to some D outcome measurements. So now, inspired by these two works and also what we saw before, we generalized the two setting to output Bell inequality, steering inequality to this scenario with n like arbitrary number of inputs for Alice and Bob and like arbitrary number of outputs. So as you can see here that, but this inequality holds only for projective measurements on Alice's side, but we don't assume any kind of projectivity on Alice's side. So, on Bob's side. So the maximum violation of this inequality is like n times t minus 1 and is achieved, for instance, by the maximally entangled state. And if your measurement is and if Bob's measurement are chosen like I star, then you can achieve this maximum bound of nd minus 1. The classical bound is in fact given like this, which is like an like the maximization over the individual expectation values of Alice's observables. So what you can see here that for this inequality to be non-trivial, which means that the quantum bound is strictly greater than the classical bound, there should not exist any common eigenvector between these measurements of Alice. So what it means is that if Alice's measurements have some common eigenvectors, even if they are incompatible, then we will not be able to see a violation of this steering inequality. So this, however, what we observed later on that our scheme of self-testing doesn't work for all such incompatible measurements which do not share an eigenvector, but a class of it, which we termed as genuinely incompatible measurements, or measurements which do not share any common invariant subspace. What it means is that if I choose some basis and write all, let's take 3 measurements, A1, A2, and A3, and write these measurements in some basis. So here I am writing it in the computational basis. So what you can see is that let us look at A1 and A2. So you can see that there are these common blocks, like A1 and A2 has this block, which is given by this, and the eigenvector and the block corresponding to this eigenvector. Similarly, A2 and A3 also has a block like this and like this, and also the eigenvector corresponding to this one. Also, A1 and A3 also have these block structures, this and this. Okay. So what it means here that each of the measurement. So if I look at A1 and A2, they can be written as direct sum of 2 matrices. A2 and A3 can also be written like direct sum of matrices of direct sum of matrices which represent the same vector space. But if you look at all the 3 measurements together, there is no common subspace in which you can write these as like direct sum. Okay. So this means that even if pairwise they are not genuinely incompatible, which means that we cannot self-test these kind of measurements, but if you take these 3 measurements together, we can actually self-test these 3 measurements. So a common example would be like Mubs, which are actually genuinely incompatible measurements. Now the main result of our work is this theorem, where let's say that if my steering inequality, which I showed before, is maximally violated, then for some state rho AB, in general we assume it to be mixed, is actually given up to some unitary transformation is given by the maximally entangled state and times some junk state, and Bob's observables up to some local unitaries are given by the conjugates of Alice's observables times some identity. Okay, so a small sketch of the proof. So as we did before. So let me go back to the inequality. So since the quantum bound is also equal to the algebraic bound, each of these terms has to be 1. So from here, what you can.
Sorry, maybe I missed that part. Like, can you hear me still?
Yes, yes.
Shubha? Sorry. Now I will have better sound. My headphones charged. Okay.
Better
Look.
questions.
What?
But now you will have better questions.
This I don't know. I cannot. Okay. Okay. What I wanted to ask. Yeah. So like in this structure, like this inequality, like did you describe what this inequality is in a sense, or like what is the it's achieved? Okay. So you just say that. So those are just those Fourier transforms, if I understand well.
Sorry.
So those are correlators.
Yes, yes. So this is written in the correlator.
I see.
Yeah. So that's why we described it before, like why we.
Okay. So like each of them. Sure. Okay. Gotcha. So I basically add expectation values of like n times d minus 1 unitaries. So okay. Yes. Gotcha. Okay. Thanks. No. So that wasn't the best question, Ramik. Yeah.
So this operator might not be unitary, because even if you assume that Alice's measurements are projective, we don't assume that Bob's measurements are actually projective, because Alice's
okay.
So we can assume on that.
But the operator norm of this BKI is at most 1. Okay. Okay. Gotcha.
So since the operator norm is 1, then from there we can actually conclude a relation like this. Okay, and first we show that to achieve the maximum violation, what you need to have is that these measurements of Bob are actually projective. Then we take a state and we write it in the Smith decomposition like this, where these lambda i's are some positive coefficients and fi are the basis corresponding to Bob's Hilbert space, and ei's are the basis corresponding to Alice's Hilbert space. And then we write this state in a form like this, where it's, as you can see, that this is like a matrix times the maximally entangled state. So we choose a unitary UB such that you can map these fi's to the conjugate of basis of Alice's basis. So that it comes into a form like a matrix times the maximally entangled state. So now what you can prove is, just for a remark, these psi ABs belongs to the support of rho AB, which the rho AB is like defined here, which is the state which is shared between Alice and Bob. So what you can prove from here that all the measurements, Alice's measurements, must commute with this matrix PA. And then for generally incompatible measurements, you can actually prove that this condition implies that your PAs is identity, which means that your state is just identity times some unitary with phi plus. So what you proved is that up to a local unitary on Bob's side, your state is actually phi plus. So now going back to the mixed state rho AB, so taking an eigen decomposition of it, it's like this, where each of these psi s are orthogonal to each other, and as shown before, you can prove that each of these psi s is actually the maximally entangled state, and with Bob's local basis given by this FIS. Okay. Now we proved that each of these bases, which is spanned by this FIS for different s, are actually pairwise orthogonal. What it means is that each of the supports of psi s on Bob's side is actually orthogonal. So then you have like you have your state, and each of this state is like phi plus on one block, then there is phi plus on another block, then there is phi plus on the other block. So it forms a block form like this, and with all the elements like phi plus. So So that's why you can write your state as like 5 plus on this times some matrix, which is like some higher dimensional matrix, which you don't which is finite but unknown. You do not know the dimension on which this row B acts. So in a similar way, you can actually conclude that your BIs are of this form. So now we look at the scenario when the measurements are not genuinely incompatible, but still give rise to the violation of the steering inequality. So, so for example, let us take these two measurements where this is just like the measurement Z in dimension 4, and this is like some other measurement with eigenvalues like 1 omega, omega square, and omega. So what you can see is that these two measurements share a block of this form, but still they do not have any common eigenvector. So this means that these two measurements give violation of the steering inequality, but we cannot certify the full measurement of this form. What you can actually certify is that the state which is shared with Alice and Bob is of a form like this. So now if these lambdas are this lambda 2 is 0, then you can only certify this part of the measurement for both the Bob's side, and if lambda 1 is 0, then you can only certify this part of the measurement on Bob's side. So in that way, you are not able to certify the full measurement on Bob's side, but only a part of it if your measurements are not genuinely incompatible. Now we also went on to prove the robustness statement of MUBs belonging to prime dimension. So for this, we take a simpler scenario where Alice just performs 2 measurements and Bob also performs 2 measurements. And so one of the measurement is of Alice is like Z, and other measurements are like the mutually unbiased basis. So for prime dimension, you can see that all the mutually unbiased bases are given here. But for non-prime, we anyway don't know what are all, we don't know all the mutual unbiased bases. So then we can prove a robustness statement that, let's say that so here, yeah, just for a note, we had to assume that my measurement on Alice's side, on Bob's side is actually projective, and the state which is shared between them is actually pure. So it was a bit weaker statement than our exact self-testing, where we don't assume that even the measurements are like on Bob is like projective, and the state shared between Alice and Bob is actually mixed. So in this scenario, if there is a
sorry, I got confused. So you have a like imperfect scenario, but you assume that one of the measurements is projective exactly, or I'm a bit confused.
So yeah, so in the first scenario, in the exact self-testing, we do not assume that Bob's measurements are actually projective. We actually prove it
right
from self-testing. But
yeah,
but in this robustness statement, which we do it for MUBs, which we have to assume that Bob's measurement is projective.
I see, but it's not very natural, right? I think, or like in a sense that for the robust thing, you would sort of guess that it's something, right? And then you would self-test that it's, I mean.
No, we don't assume like it's of some particular form, but it's just that.
Sure.
Yeah.
But this is like, but you have, okay, the score of the game is not perfect, but there is this assumption that this untrusted party performs projective measurements.
Yes.
Okay.
Yeah. So in this scenario, if let's say that I achieve a maximum violation, I achieve a violation of the steering inequality, which is very close to the quantum bound, and so then I can prove that the statistics are close to the ideal. The statistics in the non-ideal case is actually close to the ideal statistics by some factor like epsilon to the power 1/4. is not very good, but it's analytical since it works for any dimension. And the measurements are also close to the ideal measurements up to some, again, by a factor of like epsilon to the power 1/4. So now I will go to the second part of our work, where our aim was to certify any bipartite entangled state in this steering scenario. So we take a simpler scenario than I considered before. There is Alice, there is Bob, and Alice just has 2 inputs, and Bob has only 2, and Bob also has only 2 inputs. And now Alice performs like D outcome measurements, and Bob also performs D outcome measurements. So now in this scenario, we construct a steering inequality of this form. You can see, so it's kind of it's inspired from the tilted CHSH inequality. The form is very similar, where you have, so this part is the inequality which corresponds to the maximally entangled case, and then you add a marginal here, and it can give you it gives you the maximum violation from like some partially entangled states. So here these coefficients are actually dependent on the state, which will give you the maximum violation, and also on the dimension of on the local dimension of the state. So again, here Alice is trusted, and now we restrict Alice to just perform 2 measurements, which is like Z and X. Like in the previous scenario, Alice could perform like any genuinely incompatible measurements, but here it's like only Z and X. So the maximum value of this steering inequality is given by D, and for instance, it is achieved by a state of this form, where, and up, as you can see, that up to a local unitary, this is like any bipartite entangled state. And Bob's measurements are given by Z star, and B1 is given by X. Okay, so so the maximum classical value of this inequality is a bit complicated. It's given by this, where you have to optimize over these coefficients i's, which are between 0 and 1. So given any arbitrary sets of these alphas, it's not very easy to compute, but we can actually show that given any alpha i's belonging to this state, you can actually show that your classical bound is actually less than D, which says that my steering inequality is non-trivial. Now, one of the main results of this work was to prove this theorem that, to prove that, let's say that the steering inequality is maximally violated, then up to some local unitaries, I can say Bob's measurements are given by this, and the state which is shared with Alice and Bob is given by the ideal state times some junk state. So here again, we do not assume, we actually assume that there is some Eve which can actually be correlated with Alice and Bob, in the sense, so it's similar to the previous sense that there is some mixed state which is shared with Alice and Bob, and the purification lies with Eve. So just for a summary, I will just tell you the sketch of the proof. Again, we proved that.
Wait, sorry, I got confused. Like, so is that okay? But in the standard, how is it in the standard self-testing scenario? Like even in Bell inequality, like based on Bell inequality, do you allow this correlated Eve, or this kind of Eve is sort of product across Alice and Bob, and you have
so you have to prove that it's actually product across Alice and Bob. So you can
here you can't prove it somehow.
Here we can prove it. Even in the previous scenario, we can prove it, because as you can see that here is like some ABE, and it gets like separated out into the ideal state times something, which is like the ideal state is not even, it doesn't have anything with, have to do with Eve. And
gotcha. Okay.
So a small sketch of the proof would be like, we begin by proving some relations like this, that each of these terms, I will go back to the inequality, each of these terms is actually less than 1. And for the second part, this sum is actually less than 1. So we prove these two relations, and from here we can see that if we want to achieve the maximum violation of this, which is equal to D, each of these terms must be equal to 1. So then again, it implies that some relations like this. And then the whole proof just explores these two relations, and then what you can arrive at is at a relation similar to anti-commutation, but with some factor omega here. And it was proven in by Remick and Jandrek in 2019 that if this relation is satisfied by two observables, then both of these observables can be written in this form up to some local unitaries. Now we take a general state of the form like this, because now I know that Bob's Hilbert space is factored out like some d-dimensional Hilbert space times some other Hilbert space. Then you can put this state in this in these two equalities, and also put the derived measurements, and then you can find the exact form of the state, which will be something like this. So now we also wanted to see that can we actually extend this proof of projective measurements to POVMs. So what we wanted to do is, can we certify POVMs also with untrusted Bob? So it turns out that yes, we can, but for this we require that Alice performs like d squared number of measurements and Bob performs 3 measurements. So with the first 2 measurements, Alice and Bob, they certify the state which is shared between them to be a state of this form, and in the third measurement of Bob is some POVM which we want to certify. So it turns out that we cannot certify every POVM, but every rank 1 extremal POVM. So what is meant by extremal POVM is some POVM which cannot be decomposed as convex mixture of other POVMs. So like, for example, projective measurements. And every rank 1 extremal POVM can be written in this form, where this lambda b is some coefficient is between 0 and 1, and these mu's represent some projectors. Also, these POVM elements must be linearly independent and are positive semi-definite, and they sum up to identity. Now, again, we can go back to the scenario where there is some Eve, and she can actually have access to Bob's measurements and also the state which is shared with Alice and Bob. So as we proved before, that even in presence of Eve, with the first 2 measurements, we can actually certify the state which is shared between Alice, Bob, and Eve. So to be like the ideal state times some junk. Now again, what is needed is that Eve has to be undetected in whatever she does to the state or Bob's measurement, because if she gets detected, then Alice and Bob can just throw away all the runs of the experiment and start again. So then Eve won't be successful to intrude in any way their protocol. So for this, what we require is that given all the rest of the statistics, let's say that Bob performs some non-ideal POVM RB and Alice performs like all the sets of measurements like given which belongs to the Heisenberg-Weil basis. So this must be equal to some ideal POVM with these measurements. which acts on the ideal state. So now so using the first two measurements, you prove that this state which is shared with Alice, Bob, and Eve is actually this ideal state with some junk state. From there, you can actually prove that up to some local unitaries, your POVM with Bob, the non-ideal POVM with Bob is equal to some ideal POVM times identity. So these ideal POVMs are actually extremal. So I won't go into the details of the proof, but throughout the proof, we just explore this relation, and then also that IBs are actually extremal.
So actually, I wanted to ask, like, how do you control this extremality of rank 1 POVMs? Because it's a bit intricate condition, I think. I mean, it's not immediate, like if you have some effects, right? Rank 1 as you wrote, and I fully agree. Like the form is like as you wrote. Like how can you, like, I just at a high level, like your techniques and the techniques in self-testing business, they are often algebraic. So you have some manipulations of expressions, some identities that give you the magic, right? So my question is this: on high level, this linear independence doesn't, at least intuitively, doesn't fit there. Right, so how can you make use of it?
So what we say is that, let's say that I have some ideal POVM which is extremal. So I have it from before, and now I would like to characterize that there is some non-ideal POVM with Bob, and it satisfies all the statistics with some ideal POVM. And then what is that non-ideal POVM? So now how, so the assumption is that you have in your hand that some ideal extremal POVM, some statistics which belongs to this ideal extremal POVM. Yeah.
Maybe I add something. So here we assume that this RB POVM is extremal. Okay, so we have to assume it. I mean, for this proof to work, we have to assume that not only this IB is extremal, but also RB is extremal. I mean, the one that you have in the device.
I see. So you make, just like previously, you make some assumption that it's like projective in some other statements. You are making some assumption. So you are like opening a bit the this black box. Okay. Gotcha.
So now we, using this POVM, what we would like to certify is 2 log 2d bits of randomness, which is the maximum amount of randomness which can be achieved using any quantum system. So the scheme is like this, that there is some Eve who has access to like Alice and Bob, and Bob needs like log 2-3 bits of randomness to encode his measurements, and he can get like 2 log 2d bits of randomness. So since like this works for any dimension, we have like an unbounded randomness expansion. So for this, we just what we do is what we want is that Eve cannot guess Bob's outcomes with probabilities greater than 1/d squared. So if she is able to do it more than 1/d squared, this means that Eve has intruded into the system and she can guess some of the outcomes of Bob. But if it's like limited to 1/d squared, it is like purely random. So for this, we just find the guessing probability of Eve to guess Bob's outcome and say that it has to be 1/d squared, and then we find these ideal POVMs. And the amount of randomness is just given by the log of the guessing probability. So an example of this would be like this, which we constructed for like any dimension. It's a bit complicated, but yeah. So, but it's at the end of the day, it's like just some coefficient with some projectors. So now we also constructed a scenario where we can convert this one-sided device independent scenario to a fully device independent scenario. So as I said before, that the only difference between Bell scenario and steering scenario is that you assume the measurements which Alice performs, or Alice is trusted. So now if you find a way to certify Alice's measurements, then the whole scheme in a fully device independent way, then this whole scheme will be like fully device independent. So in our scheme, we assume that Alice performs X and Z. So if there is some way to fully device independently certify X and Z, so that means that this full scheme will be like this scheme to certify every bipartite entangled state will be fully device independent. So for this, you have a preparation device. You again have Alice, you have Bob. Alice can choose some inputs and Bob can choose some inputs. And Alice and the preparation device has now two inputs. So now the preparation device prepares two states. So depending on the state, you collect all the statistics, and with the first statistics you violate some inequality, some Bell inequality, whose maximum violation is given by X and Z, and then using that you can actually certify. You can use the steering scenario with this preparation to certify any bipartite entangled state in a fully device independent way. So, however, there is no such scheme till now which can actually certify X and Z for any dimension. However, for D equal to 3, there is a scheme, but the problem there is about some transposition, that even Z and X can give you the maximum violation, also Z and X transpose can give you the maximum violation. And that is the reason that we couldn't like prove this extended Bell scenario till now, but this is like a general idea to make our one-sided device independent scheme like fully device independent. Yeah, so for concluding remarks, we proposed a method for certification of large class of D outcome projective measurements, which we termed as generally incompatible and the maximally entangled state of two qubits in one-sided device independent scenario. So this is the first self-testing scheme which applies to mutually unbiased basis of any dimension. In particular, it even allows for robust self-testing of mutually unbiased basis in prime dimension. We discussed the case when the measurements were not generally incompatible, and then we concluded that only a part of the measurement could be characterized. So the details of the first work can be found in this archive paper, which is still under review. The second part of the talk, which we constructed a class of steering inequalities, which is maximally violated by every entangled state and a pair of mutually unbiased bases. Then we provided a method to certify the quantum realizations with that maximally violated steering inequalities, which are like every bipartite entangled state and mutually unbiased bases. Then using these results, we were able to certify any rank 1 extremal POVM. And then we used it to show show that the maximum amount of randomness, 2 log 2 d bits of randomness, can be certified through our protocol. And this work is under preparation and it's almost done. So we hopefully will submit it by next week, or this week. Yeah, so that was it. And my colleagues, so here is Remik and Deba, Yakub, Jeba, and Ovidush. I didn't have a picture of Ovidush, so so all of them are involved in these two works. So, and that's all from my side. Thank you.
Thank you very much, Bayan. Yes, we have time for questions, comments, remarks. Okay, I have some question. Like I'm a bit confused about those additional assumptions for, like, first for robust self-testing when you assume projectivity on the Bob side. Second, in this self-testing of POVM of extremal POVMs, you assume that actually what Bob does is extremal. So like technically, why do you need this? And is it fair then to call it? I mean, okay, it's some form of like self-testing under some weaker assumptions. Agreeable, but it's not something what would like in the ideal scenario, right? So yeah, how to think about all this? Yeah.
So for projectivity, I would say that in a way, let's say that we have some, because we don't assume any dimension on Bob's side, and if there is no Eve, then it's completely fine to assume like projective measurements, because we can always purify the state on Bob's side, and then like because you have this freedom of dimensions, you can always assume it to projective measurements. But if there is some Eve, then sure, yeah, this assumption of projectivity is weak, and then and this assumption on extremality is something which it's weaker, but we were not able to find any proof which do not assume that it's without assuming that this POVM is extremal. We were not able to find any proof that could certify this. So there is no as such like why do we need to assume that Bob's POVM is extremal? But
maybe I add something. So I just made a mistake about this extremality. So we only assume that IB is extremal. Okay, we don't assume
only the ideal POVM is extremal, but I guess that's what you were asking, right? That why IBs need to be extremal.
No, then I understand why. I mean, if you don't, then it can be a mixture, right? Of strategies.
Yeah.
Sure. Okay. So then then my question was had a bad premise. Yeah. Okay. I understand.
Maybe I will add something on the other of your questions. So concerning the assumption that the state is pure and the measurements are projective. So you're right that we should infer it from like violation of our inequality. So, and like we were pushed by the referee to prove all our statements for mixed states and non-projective measurements. Okay, so this is what we managed to do for the exact case. Then we were thinking that I mean, these robustness statements are always weak if you prove them analytically, because the scaling with epsilon is very bad. Okay.
Yeah.
So this is not a robustness statement. This is just continuity statement. It's just to tell you that if you depart a bit from the maximal violation, I mean, the state is still close to the state maximally violating, and the same for the measurements. Okay. So it's much better to do it with SDP, I guess. But we didn't do that, so we left this just to show that there is discontinuity, and that's it. Okay, but it's true that we shouldn't assume that the state is pure. It's not even an assumption, I would say, because you can always purify everything. Okay, so you can always realize this violation with a pure state. Okay.
Right.
And in fact, in an experiment, you will not be able to distinguish which kind of realization you have.
Right. Okay. I was actually a bit confused. Right. I mean, okay. How to phrase it? Like, yeah, because like if this Bob is like untrusted, then of course you can sort of purify everything on his side. But then I was like a bit confused because like in standard scenarios, you don't have this if you are correlated to, and I'm a bit kind of puzzled about.
But now if is just environment which gives you purification of your mixed state, so it's like equivalent. I mean,
I see.
So in one paper we call it like rho AB, and in the other one we call it psi ABE, and we do this because we have randomness certification.
Oh, you had different referees.
No. This paper we are still writing. So.
Okay. Right. Can I have just one last question about because I'm always interested in those high-dimensional POVMs for whatever reasons. Can I see like this POVM that you constructed?
Well, you can, no? It's in the paper.
Right. So it's like extremal discord, Okay. I even made a picture for myself, like, because like we might want to type
maybe together
something.
with us. Together with us. Okay?
Yeah. Yes. Happily, yes. So, what is this POVM intuitively like? Because we actually have now and then some high-dimensional POVMs, but I know like either you have SIG POVM or you have some covariant POVMs in arbitrary D, or random POVMs. Those are the ones that kind of I came across when it comes to high-dimensional POVM. So what is this guy?
So here we just found out these like these states and these coefficients with some like imposing this constraint, like that given any outcome you have, like you put the state and you get like 1 by d square, and then these have to be like linearly independent and they sum up to identity, and that's it. So I don't know whether like they have some special POVMs in some higher dimension, but
so that it's they depend on some parameter, on a bunch of parameters, right? On those.
So like these depends on these parameters. So, and these parameters we found by like using.
Wait. So what they depend on what? Like what are the okay? Like it's new, and what else B? No.
So so it depends on like this lambda B and this state delta B. So
I see. Because lambda is also a parameter that you set.
Yeah. So
okay, cool. That's a nice. Okay, cool. Nice. Okay, we come back to you if when we want to like play with it. Okay. Yes. Okay. Are there any other comments or questions to Shubha or Remik?
Maybe I would add a comment about on this assumption of that the state is pure.
Yeah.
So usually people assume that the state is pure because it's very difficult to prove it when it's mixed. Okay, so I mean,
it's difficult to prove what?
I mean, this self-testing statements.
Right.
So, for instance, even in in Berlin locality, people usually assume the state to be pure because the proofs are very difficult. And well, I know one by myself and Jędrek.
Right.
It doesn't assume it, okay? And it's like for two concrete states, so it's like in a particular case.
Right.
So here we like in the steering scenario we kind of managed to avoid this assumption, okay? Because one part is trusted and everything gets much simpler. But in non-locality, it's always difficult to prove this kind of statements.
But
so I kind of understand that people assume it, okay?
But okay, in non-local, I'm a bit. You mean, but what? Like in non-locality, if your state is mixed, then you cannot self-test, right?
No, why not? Look, so for
wait,
instance,
wait. No, it's a different question, right? Gotcha.
So for instance, the state that Shubhayan showed is like the tensor product of the maximally entangled state of two qubits and some mixed state. So overall, the state is mixed.
Yeah.
Right. Yeah, okay, because typically those things are based on like violation of some Bell inequalities, and to have this violation, you have to be extremal, like kind of, and this is how it's tailored. But of course, you can just generally ask a question, you observe some correlations, and like are like whether by doing some, and you ask whether by doing some local rotations, you recover the state up to isometry, and it's still well posed question. Gotcha. Right. Cool. So, right. Just a quick comment, because we have some. No, okay. This is a comment I will go like offline. Like, yeah. because it's like technical. I might want to talk to you, Remik or Shuba, about it. Yeah, okay. So I guess like if there are no further questions, we can thank the speaker again for a nice talk and sharing his results with us.